Okay. Okay, good. So what we have been doing is our aim is to define a measure and the concept of measure. So for that we cannot define. I mean, since we cannot define the measure on all subsets of some universal set, so we want to restrict to some subclass of subset. So for that we needed some very nice objects called nice collection of subsets, so that we called as sigma algebras and algebra. As I said, we will be defining our measure on sigma algebras. But since sigma algebra is too complicated, we will define on an algebra and then extend it. So this algebra is a tool, as I said, it's a tool to tool to construct our measure. So there is another tool which is what is called monotone class. Okay, so this is also something like algebra, something like sigma algebra. There is something else called monotone class. So we want to define this monotone class first. So this is something we will be using. I mean, this is once we have a monotone class, then we prove a theorem relating monotone class and algebra, sigma algebra generated by an algebra. So then that's called monotone class theorem. That's what we are going to prove now. So this will be later helpful to when we prove theorem. This will be helpful. So for that we want to define a monotone class. So we have defined algebra. A monotone class is just this. So let's denote it by M. A family script M, okay, is a monotone class. Monotone class. If it satisfies the following. So if one condition, first condition, it is, I mean, it is just a monotone, something is a monotone class if it is closed under increasing union and closed under decreasing intersection. That's all. So if you have a AN collection which is contained in M, okay, and AN increasing to A, then union of AN, N equal to 1 to infinity, maybe call it N equal to 1 to infinity, and this is also in M. Okay. Similarly, if we have a BN, a collection which is contained in M, and Bn decreasing to B. So we know what is increasing, what is decreasing. One is contained in the other one. It's a increasing union, and this is decreasing intersection. So then intersection of Bn is also in M. Okay. So a class, a set of, a collection of subsets of some X. Okay. Maybe you can say that M is a monotone class of subsets of X. X is any set. Okay, you take X any set, then you a family of collection of subsets of X is called a monotone class if it is closed under increasing union and decreasing intersection. That's what we call as a monotone class. Okay. And of course, a sigma algebra is certainly a monotone class, which is closed under any countable union. So it will contain this. So sigma algebra is a monotone class, of course. So once we have defined this, we want to connect an algebra and a monotone class. This concept of an algebra, which we have defined, which is closed under finite union, we want to connect that with sigma algebra and monotone class. So that is this theorem, or it's usually called lemma, but it's a proposition here. I mean, since it's used to prove theorem, but here let us call it a proposition. This is what is called the monotone class lemma. Monotone class lemma. Okay, so I will not write. I mean, we always assume there is a set X, universal set X. So I will not write it again. So let A be an, let me write it, algebra of subsets of some X. Okay. Then we have defined, so if we have any collection of subsets, we have defined a sigma algebra generated by that. It is just the smallest sigma algebra containing that class, which is also same as taking the all intersection of all sigma algebras containing that. So that will be the smallest one. So it's well defined. And so sigma algebra generated by A is also same as the monotone class generated by A. So if you want to know, just a remark, yeah, M of A is the smallest monotone class. Similar to, it's same as sigma algebra, smallest to monotone class containing, this is not net, there is no need for it to be an algebra containing, for any class of subsets you can take, containing A. I mean, this is containing, and the handwriting is not generally not good, but first time I'm writing on these things. So containing A. And this is actually equal to intersection of all M, okay, such that A is contained in M. Okay, that is how it is defined. Okay, you take all monotone class, and where M is a monotone class. You take all monotone class which contains A and take the intersection, and that, I mean, and there is one monotone class, of course. You take all subsets, the power set. So that is actually that satisfies all axioms. So that is a monotone class. You just take the intersection of all those things. So there exists one. So this intersection is well defined, and you have the concept called monotone class generated by something. So here the theorem is, if you have an algebra, then the monotone class, I mean, you don't need, I mean, if you want to verify, you want to see something is a sigma algebra, you don't need to verify that I mean, it's closed under arbitrary countable union. It's just, you just have to take union, I mean, increasing union and decreasing intersection. So because of that usefulness, we prove this theorem. A sigma algebra generated by an algebra is same as monotone class generated by the algebra. Proof. So what do we have to prove? So we want to prove that sigma algebra generated by this. So we already know that this. So this is any sigma algebra is a monotone class. So a sigma algebra generated by A will contain the monotone class A. So it's clearly that sigma algebra generated by A contains the monotone class generated by A, because sigma algebra itself is a monotone class. So this is a bigger monotone class. So this is a monotone class. So this is a sigma algebra generated. This is a monotone class. So this is a bigger monotone class. So that will certainly contain this monotone class generated by that. So that's why this is true. Okay. So now, so what we want to prove is, now we want to prove that this. Now we want to prove that this. We want to prove the other way. So to prove MA, so this is what we have to prove, contained in sigma A. So it is enough to prove.
Sir, the other inclusion.
Yeah, say it again.
The other inclusion. I mean, we want to
The other
prove.
inclusion was we are proving. The other inclusion is monotone class generated by. Oh, sorry, I have written it the other way. Okay, sorry. Correct. Good, thanks. So we want to prove. Yeah, we want to prove the monotone class contains a sigma algebra generated by that. So it is enough to prove that this is a sigma algebra. It is enough to prove this is a sigma algebra. Okay. So if you prove this is a sigma algebra, and that is a sigma algebra which contains that script A, the algebra. So it has to contain any sigma algebra containing minimal sigma algebra. So this will form. It's enough to prove that this is a sigma algebra. So to prove that this is a sigma algebra, we have to, so first, we want to prove this. So to prove that this is a sigma algebra, we have to prove that this is already a monotone class. So we have to prove that it is closed under complements and it's closed under countable union. So to prove that something is closed under, so first let's so to prove this, enough to prove. When I write this ETP, that means enough to prove one. This MA is closed under. If you don't understand my handwriting, you tell me. I will erase it and write it again. Okay, it's closed under complements. Okay. Then the second thing is, so we will verify, we will prove that this is enough to prove. I mean, first we will verify that it's enough to prove this. Of course, we have to prove that it's enough to prove. I mean, complements we have to prove, and that's first statement. The second statement is, So the second statement is closed under union. Union means just two union. I mean, I'm not saying countable union. It's enough to prove. So if it is closed under union, that means you just take two of them and then take the union. If it is closed under that, then by induction it's closed under finite union. We want to prove that it is actually closed under countable union, countably infinite union. So why is that true? If you have any countable union, then you can write it as a increasing union, of course. Okay. So if the finite union, so if so let an is anything which is contained in M of a, okay, then let bn equal to union of m equal to 1 to n an, okay, then bn increases to union of an, of course. Okay, I mean union, or we can write it like this: union of n equal to 1 to infinity bn is same as union of n equal to 1 to infinity an. So this is an increasing union. But since this is a monotone class, if we prove that this bn is in the monotone class, then it is true that the increasing union of bn, which is equal to union of an, is also there. So this is because of that. Since if there is an, then let bn is like this, then this is true. Okay, so it's enough to prove second thing, it's closed under finite union. To prove it's closed under finite union, it is enough to prove that it's closed under two unions, a union b. It's enough to prove that. Okay, by induction it will be true for finite union. Then by, because of it's a monotone class, any countable union can be written as increasing union. So because of that, this is true. So it is enough to prove it's closed under complement, and then it is enough to prove that, enough to prove this. Okay. So we prove the first one. Okay. The first claim, that is m of a is closed under complements. Okay. This is our proof. Proof of one. Okay. This is proof of one. M of A is closed under complements. So to prove that, I mean, this is in measure theory, this idea will repeat again and again. The idea is, if you want to prove something, then you take the connection which satisfies that and prove that that's a sigma algebra. So then the whole sigma algebra will satisfy that. To prove that, so let you define something called MC. I mean, I'm using M again and again, but you know that M of A is the sigma. That's what we want. I mean, this M of A is the monotone class generated by A. This MC is something different. So that is all those sets in E in M of A, such that E complement is also in M of A. Okay. You want to prove that. So the first you prove that. You want to prove that MC is equal to M of A. That's what you want to prove. To prove that, it is enough to prove that MC is a monotone class and A is contained in that. So then it will imply that the monotone class generated by that will be containing in this. But this is already contained in that. Then okay, let's write step by step. If we define MC like this, but by definition we are taking sets in M of A. So then MC is certainly contained in that by definition. Okay. Now to prove MA is contained in MC, it is enough to prove MC is a monotone class. Okay. If we prove MC is a monotone class, then since MA is the monotone class, minimal monotone class containing the K, and it's enough to monotone class, and A is contained in, and oh no. A is contained in MC. Okay. Now A is certainly contained in MC. This is clear. Okay. That's because A is closed under complement. So this is clear. A is contained in MC. We have to prove that MC is a monotone class. That's what we have to prove. So to prove MC is a monotone class, what should we do? Suppose if so, let AN contained in MC and AN increases to A. Okay. Okay. Then because by definition AN is in MC, then AN complement is in MC, and AN complement will decrease to A complement, right? AN decreases to, sorry, this is not script A, this is ordinary A. So, suppose we have a collection AN increases to A, then AN complement is also there because AN is in MC, AN complement is also there, and AN complement will decreases to this. Okay, right. Then union of union of AN is in M of A, and union of AN complement, which is same as intersection of AN complement, which is also in M of A. Okay, so this implies union AN complement is also in MC. It's all, MC is a collection of all sets which is in M of A, such that its complement is also there. So here the complement is also there. This implies this is in MC. That's what it means. Okay, so MC is closed under complements. That's what you have proved. Okay, so that's what you have proved. So claim 1 is proved. MC is closed under complement. Now we want to prove the other way. So we want to prove the other assertion. 2, proof of 2. That is MC is closed under union. So as we have already noticed, MC is closed under union means it's closed under finite union. Then if it is closed under finite union, then because it's a monotone class, the countable union is also there. That's what we have checked. So we want to prove. So suppose we want to prove that if you have A and B in MC, then A union B is also in MC. If A has a complement in M of A, B has a complement in M of A, the union also has. That's what we want to prove. So to prove that, let's check, take a set in A. Okay. Okay. No, let's not take the set in A. I'll erase this, I'm sorry. So define for any set, for any, maybe I call it E in M of A, define ME. Okay, I think these notations are okay. These are different things. Okay, I'm using the letter letter M to denote the monotone class, but these are all different objects. ME, MC, and M of A, all those things. Define ME equal to all those set in, let's call it A. A is okay. A in M of A. Okay, such that A union, maybe I call this A and UE. That's okay. A. Okay, I will, if you don't mind, or you can keep it. I don't mind. Okay, I will change this to A and E. Call this A, and this is E. Okay, such that A union E is also in M of A. Okay, I take this collection. I want to prove that it is closed under union. I just want to use the techniques of, it's a techniques of, we are in a convenient situation. Techniques of monotone class or tree. You want to prove something is a monotone class. So then I define like this. Okay. Then I claim the following. Then,
sir.
Yeah.
In the first
You are defining this MA for any arbitrary set.
Yeah, any arbitrary set A, right? That's what that's what I am defining first. Okay. Then I will take an algebra A. Then I will take a set in A. Okay. Then I will prove something for that, and then I will prove something for that. So suppose This is I'm defining this monotone class I'm defining for any A. Okay. So suppose this A is in
So first line will be for any A in MA.
first line. Which line? This line?
First line of proof 2. Yeah.
Here.
Yeah. That.
Ah, sorry. You want to change this? Yeah, because I changed it, right? Yeah, that's right. Suppose for any A in M of A, we define like this. Then we want to, then suppose A is in A, okay? So that's why you wanted to use the letter A, capital letter A for that. Then suppose if we have something like this, then okay, then MA clearly contains A. Okay. MA clearly, I mean, MA, so if we fix a set A in A, then MA is all those sets whose when you take the union with A, that has to be in there. But when E is in the script A, E is in the algebra, then this union is certainly there. So MA contains the algebra A. Okay, that's right. And and MA is a monotone class. Monotones. You need E, no? Okay. So, I mean, I'm defining this M subscript A like this. Then for any A in the algebra A, this MA contains A. That's because the algebra is closed under union. So because MA is contained in the A. And this MA is a monotone class. That's very easy to check. That's because if you have any En increasing to E, then we have that A union En will increase to A union E, right? Okay. But this A union En is in, suppose if you have in, you assume En increases to A and En is in M of MA. Okay. M subscript A. This is not so this is maybe confusing. This M subscript A. Suppose if you have En is there, that means that A union En is in M of A. That means this is in M of A. So because this is a monotone class, this is in M of A. Since M of A is monotone class. Okay. Okay. So it's because of that. So it's clear. I have just verified this. MA is a monotone class. Similarly, intersection also. Similarly, if Fn is in MA, okay, that means okay, let's write the proof here. A union Fn is in M of A, that's what it means. Okay. Then A union Fn, this intersection, okay, this intersection equal to A union F, and Fn decreases to F. Okay. This is equal to F union, okay, it's okay, I written F union A. So then these things are in M of A. Since M of A is a monotone class, this is also in M of A. Is that clear? Okay. Is there a problem? This is okay, no?
Yes, this is fine.
This is clear. I mean, we are doing the routine thing, but you have to be careful with your argument. That's all. Okay. Yeah.
Sir,
Yeah.
sir,
Yeah.
can you say again what is written here? Like, and so suppose A belongs to A, then
A belongs to A. Yeah.
then M of A contains A.
That's yeah. Is that clear?
Yeah, and M of A is monotone class, is it?
MA is monotone class. Okay, you have to verify MA is a monotone class. M subscript A. I mean, see, while saying it's confusing because M subscript A is what I have defined above. and M of A, M script A is something else. That's a monotone class generated by A. Okay. So M subscript A is monotone class. That's what I have to verify. So to verify it's a monotone class, you have to prove that it's closed under increasing union and decreasing intersection. That's all. So it's closed under increasing union means what? You have a collection En, which is in that M subscript A. Then you have to prove that that union is also there. So that is in M subscript A means that M, that means it's precisely the statement, right? It's maybe I will use a color. Then I have to find it. So let me use a color. Okay, so do you understand? Shall I go through the explanation?
Excuse me.
Yeah.
Why are you using the fact that the algebra A is contained in MA?
No, that is something we are very. That's because we want to prove that that is a monotone class. That is MA. We want to prove that this MA is equal to that. See, we want to prove that this M subscript A is equal to M of A. That's what we want to prove. We are not using it in the following. We are using it. I mean, what proof of two? What is the proof? We are proving. See, let me go one by one. We want to prove this. We want to prove this, right? We want to prove this. I will put it in red color. We want to prove 2. 2 is it's closed under union. That's what we want to prove. To prove that, we are first defining this MA like this. Okay. Then we want to prove that this MA is nothing but equal to this M of A. This MA and this M of A are equal. That's what we want to prove. Right? So once we prove, then we want to do something else to prove that, I mean, it's whatever is closed under union is exactly that. That's what we want to prove later. I mean, there's one more step. So first step is to prove. So this is the first step. So for any A, we are defining this MA. Then the claim is maybe the claim. Okay, let me write claim. MA equal to M of A. This is our claim. So to prove this claim MA equal to M of A, we have to do 2 things. One is you verify that this A is contained in this MA. Then you prove that it's MA is a monotone. These are the 2 things you have to verify. Okay. Now it's clear where I am using this.
Yeah, yes, sir.
Now it's clear. So we have verified that A is contained in MA. Script A is contained in M subscript capital letter A. Okay. So then we are proving that this M subscript A is a monotone class. So that's an easy verification. To prove that M subscript A is a monotone class, you have to take some En, which is increasing to some E. Then A union En is in M of A. That's what it means. That's the definition. Then the union is also there because that is a monotone class. Something else is a monotone. You just have to be careful. If the statement all follows immediately by definition, it is just you have to see the meaning clearly and write it. Okay, careful. That's all. So that's how we have got it. So similarly, the intersection also. So we have proved that. Hence, now I change the color. Yeah. Hence, oh, it hasn't changed. Okay. Hence, MA is equal to M of A. Okay, right. So this is for all A. We have proved that this is for all something in algebra. That's what you have to prove. Okay, we have assumed that A is in script A and then proved this. Okay. Now the next claim is this was finally, I am again confusing, but there is not much choice. Let's take M equal to all those A in M of script A. Okay, such that this MA is equal to M of A. Okay, is that clear? The statement is clear. You take all those elements A, then. So now, this is the statement. Now, to prove M of A is closed under unions, it is enough to prove M is equal to MA. Okay, it's clear. Once you prove that, that is the definition. Okay. What is M is defined as all those A such that MA equal to MA. That means that MA if you take any set in this and take the union with A, then that is an M of A. That's what it means. Correct? You want to prove, see, now our aim is to prove 2, the assertion 2. The assertion 2 says that M of script A, this is closed under union. To prove that it's closed under 2 element union, A union B. So for that it is enough to prove that this script M is same as script A. Why is this true? Because if we prove that, then you take any element A in M of A, then this MA is equal to this. That's what it means. Okay. What does that mean? That means you take any other set in M of A, B or something in M of A, then that A union B is again in that. Okay, so this is what you do. Just think about it. It's clear. Anybody has a doubt in that?
So we are showing that finite union. So MA is closed under finite unions, right?
MA is closed under finite union. That's what we want to prove.
So for that we are
No,
showing
MA is closed under finite union. MA is closed under finite union. That's what we want to prove. Initially, MA is not closed under finite union. It's a monotone class. It's closed under increasing union. We want to prove that it's closed under finite union when A is an algebra. That's the whole thing we want to prove. To prove it's closed under finite union, we are proving it's closed under 2 union, because by induction, you can prove it's closed under finite union. You can take induction, go one by one, and you can do that. If it's closed under 2 union, then by taking one other union, closed under 3 union, then 4 union, 5 union, you can go on like that. So it's closed under any union, any finite union. Okay. So as initially remarked, we have to prove it's closed under 2 union. 2. So for that only we are working all these things. To prove closed under 2 union, we have to prove that for that purpose, we defined this M subscript A, which is here. Okay, we defined this. Okay. So using that, then we proved that the algebra A is contained in that. That's first thing we proved. When A is in that. Now we are proving that, so because of that, this algebra A is contained in that. So now we want to prove this assertion. This script M, whatever we have here, that is equal to this M of A itself. That's what we want to prove. If we prove this, then our assertion that M of A is closed under union is proved. Okay. So is it okay with everyone, or you want to think about it? There is really, you have to just think. There is really nothing complicated in this. You go through the argument. If you want, let me try to go through it myself. Okay. I want to prove that this script MA, this is closed under finite union. So for that, I am proving that it's closed under 2 union. So suppose if I prove this, then this M equal to this. That means all these MAs are equal to MA. That's what it means. Suppose I prove this M equal to M of A, then all this M subscript A is equal to that. Maybe I will change color and then go one by one. Suppose if I prove this, okay, if I prove this, then let's prove that for all A in MA, this is true. But this is true means what? This is by definition all those set whose union is in M of A. Okay, all those set, if you take the union with A, that is in M of A. That means that A union B is there and for all those sets. But this is true for all, this is true for all sets in A. This means that A union B is there. It's closed under union. Okay, it's a direct thing. So to prove this, you just have to verify that this is a, again, so this is, so now, okay, so now we are enough to prove this. Now this M is nothing but is all those things. By definition, EA in M of A such that E union A is in M of A I'm also getting confused with small a and script A and this. Okay, M of A for all right. This is what we want to prove. That's what M is. Okay, M by definition is this. If you write the definition, that is what is this. Okay. Okay. Now that you just have to verify it. So now to prove that, enough to prove this. Now we want to prove this. Okay, to prove this, maybe you call it star. So now to prove star, enough to prove M is a monotone class. Again, the same thing. Okay. We have checked that M of A contains A. That's what the first step. We have checked that. It's here. Where is it? Yeah, we have checked here. Okay, it's here. If you read, okay, it's here. So now we want to prove that it's enough to prove that it's a monotone class. So it's a monotone class which contains script A. So that it should be equal to M of A. So what does it mean to prove it's a monotone class? It's closed under increasing union, and this that is just clear, no? So if suppose some En increases to E and En is in M, okay, then okay, then what does it mean? Then we have to verify this property. What I have written, okay? No, wait. Sorry. Let me be very careful. So we want to prove that M is a monotone class. Suppose let's take this. An contains in M and An increases to A. Then we want to verify this A is there. Okay. So An is in M means this means An union E is in M of A for all E. Okay. That's right. Okay. Now union of An union E increases to A union E. So now all these things are in M of A. This implies that this is also in M of A. Okay. This implies A is in this A union E. Okay. This implies A is in M. Just write the definition, it will come. Okay. Similarly for intersection. Similarly, if you have a Bn which is contained in M and Bn decreases to B, okay, it's contained in M. Bn is in M. Is in M means Bn union E is in M of A. Okay. Now Bn decreases to that, then Bn union E decreases to B union E. Right? So now all these things are in M of A. But since M of A is a monotone class, this is a monotone class. This implies B union is also in M of A. This implies M of M is a monotone class, which implies M is equal to M of A. That's what we want to prove. Okay. So the theorem is proved. Okay. I suggest you sit and verify this. Okay. I mean, convince yourself. All the arguments are there. There is really nothing complicated about this. It's just direct. Is there a problem?
So it should be BN union E, not EN.
BN union?
E. Now 1, 2, 3.
Say it
Fourth
again.
line. BN union E. And the fourth line from the bottom.
Want to BN union E. Correct. Sorry. There is no EN. Now it's clear. Okay. Good. Okay. Yeah. So except my handwriting, the proof is written very clearly. Okay. The way I have written all those things, apart from that, it's written, everything is written. Okay. So the proof is okay. So this is the monotone class lemma, monotone class theorem or monotone class lemma, which we want to use. Okay. But what is our aim? Our aim is to extend. So this is what we want to do. We want to extend. So we have, first we want to define a measure on an algebra. For example, when we define the Lebesgue measure is just a extension of length. When you have Lebesgue measure on real line, which is just a generalization of length. When you want to define Lebesgue measure in R2, that's a generalization of area. So generalization means we can define for any, it's not just for interval or something, we can define for complicated subsets. So that's what it means. So our extension of length and area, which is the Lebesgue measure. So we want to define the Lebesgue measure for real line. Then we want to define Lebesgue measure for R2, R3. So to do that, we want to define on an algebra. We have already defined an algebra, disjoint union of half closed, half open intervals. We have taken, that's an algebra. Sorry, finite union of half closed, half open intervals, which we define, which is an algebra. So we want to define the Lebesgue measure on that algebra by in the obvious way. Then we want to extend it to a sigma algebra generated by that algebra. So we want to consider the general process. If you define a measure on an algebra, then we want to define it, extend it to a sigma algebra generated by that. So that's what we want to do. So how we define it, how we extend, that is the problem. So in some, I mean, at some point, if the screen goes or something, you remind me. Okay, I may not notice. The screen is there. Okay. Okay. So how we want to define? First, we want to define. So this is what is called outer measure. So I'm doing something new. Okay. So our aim is to extend a sigma additive. We don't call it as a measure. We want to have a sigma. We define what is called a sigma additive function. Sigma additive function on an algebra to a measure. We defined a measure and a sigma algebra. So to a measure on the sigma algebra, and this is an algebra A, let's call it A. Then we want to define the sigma algebra generated by A. Okay. So if we have a sigma additive function defined on algebra, we want to extend it to a measure on the sigma algebra generated by A. Sigma additive is countably additive. Okay. So that is what is called outer measure. I mean, not the measure is not called outer measure. This outer measure is something which is defined on all subsets. First, we will extend it to all subsets, but that will not be a measure, which is what is called an outer measure. It will not be countably additive. Okay. So then we will restrict to a subclass, which will contain that algebra, which will certainly contain the sigma algebra generated by that. I mean, it will be a much larger sigma algebra actually, but we will, so in particular, it will contain the sigma algebra generated by that. And there we will have, sigma additivity. It will be a measure. Okay. So this is what is called outer measure. And this extension process is called Carathéodory extension. So let me write. Hopefully the spelling is correct. Carathéodory, A or O. I think it's O. Carathéodory extension. So this is the Carathéodory extension of a sigma additive function on an algebra A. So suppose, let's fix here. So let's call that also mu. Okay, fix here sigma additive function mu on an algebra A. Okay, we have an algebra A, and that we have a sigma additive function. This mu looks like m. Okay, I'll erase it. Okay, this is mu. Okay, we have a function mu, which is we have defined sigma additive function on the algebra, and we want to extend it to a sigma algebra generated by that. Okay, then define mu star A. Maybe I will write it here. This is what is called outer measure. Okay, please don't write. I have written it wrongly. Mu star E. Okay. Not script A. Mu star E equal to. I have to take infimum. Infimum of. Let's come to the infimum. Summation n equal to 1 to infinity mu of an. Okay, where an from n equal to 1 to infinity is contained in that state. It's a countable union. Okay, infimum over, here I will write it, all this. It's infimum over this, all this. Okay, now it's clear. Such that E is contained in union. Okay, now it's clearly written. So if you have any set, define for any E. We have our original set X, sigma algebra, okay, sigma E contained in X. Okay. You start with any set X, then you consider the algebra of subsets of X. Okay. Then for any set in E, any set in X, you define mu star E, mu upper star E, which is the infimum taken over all countable collection in the algebra, which covers this, okay, which is a countable cover for this E, which covers this, and you take the sum of this, sum of n equal to 1 to infinity mu of A. We are not assuming it's disjoint or something. That will be contained in all those. The statement will be contained with that. Because we are taking infimum. If you take disjoint, that will be less than that. So it's okay. We are taking infimum. This is what is outer measure, because we are approximating from the top, okay, which is outer measure. You can define inner measure also, but there will be some difficulty in inner measure. If it is, I think there will be, because of the increasing, I mean, we need finiteness. If it measure, if the sigma dt function is finite, then it will be okay. But this works for any infinite thing. So we usually use the outer measure. Okay, inner measure and outer measure will be equal when mu is finite or something. Okay.
Sir, can you
Hmm?
can you rewrite what you wrote under infimum? Like it's not very clear actually.
Shall I write it again? Okay.
Yeah.
Let me write it in a bracket so that the whole thing will be clear. This is the infimum. So here it's clear. It's the infimum of this number, which is just a number n equal to 1 to infinity mu of an, where E, where first thing is an. It's a collection which is contained in algebra A, okay, with n equal to 1 to infinity, such that this is a symbol for such that, I hope everybody knows, such that E is contained in union of A. Is clear? Okay, this is infimum over this. Okay, it's clear. You take any countable collection from the algebra which covers the set E, then you take consider the summation, and you take the infimum of all those summation, all those numbers, okay, which clearly exist. It may be infinity. If it is infinity for everything, then it will be, infimum is also infinity. Okay, I mean, certainly this cover exists because the universal set is there. So that will contain this. So that will be in the algebra. So this collection is not empty. Okay, this collection is not empty since X is in A. Okay, I mean, you can take the countable collection, but you can take the countable collection to be X empty set, empty set, empty set. You can take finite collection, finite union also, finite cover also. It's okay, because you can attach empty sets and do that. So this is okay. There is no need that it has to be strictly infinite. It can be finite also. Okay. So this is how the outer measure is defined. Now we have a long way to go. We want to prove several lemmas and finally prove that this can be restricted to a sigma algebra. So what do we prove? So our strategy, our aim, our aim is to prove first one, mu star restricted to this A is just mu. That is one thing we have to verify, because that's what we want to extend. Two, mu star restricted to the sigma algebra A I mean, this is defined on all subsets. This mu star is defined for any subset. So is a measure. Okay. That's what we want to prove. Okay. But we will be doing something more. We will be defining on a bigger sigma algebra than the sigma of A. Okay. That's what we will be proving. So we will go one by one. What's the time? 4:23. So I will have time to prove few proposition, one or two proposition. First, easy proposition. Proposition 1. I'm not numbering. If you want, you can number the proposition, okay? Because I will not remember the numbering. So first thing is 1. It changed to eraser. Mu star restricted to this A is mu. Okay, that's what we want to prove. I mean, that means mu star of A equal to mu of A for all A in script A. That's what it means. Okay. Then the second one. So, I mean, that's one thing we want to verify. Okay. Then we have defined what is called subadditivity. Okay, if you remember. I mean, any countably additive function is also subadditivity. We have proved that. So mu star is subadditive. What does it mean? That is mu star of union of En is less than or equal to summation En. Okay. It is just subadditivity. I mean, this is for all. Okay. We take that. This is true for all power sets. It's subadditive on the power set. Okay. So we have the outer measure, which is subadditive, but it will not be additive. I mean, it will not be sigma additive. Okay. That is our problem. That is why we cannot take the power set. Okay. The first one, you want to prove that this is okay. So how is this mu star defined? That is defined as an infimum. So the first thing is that so if we take for A in script A, okay, A of course looks like this: A union empty set, union empty set, union. Okay, like this. Okay, it goes on like this. Everywhere it's empty set. Okay, so this implies mu star E, which is the infimum of all those things. Okay, infimum of any such collection. So this implies this is less than or equal to, by taking this cover, this also of course covers, okay, mu of A. This is clear. Okay, there's nothing in the argument. This mu star is defined as the infimum of all those numbers. You take in that you take A1 equal to A and A2 everything as empty set. Okay, that is one such cover.
Sir, what is E in the proof?
Let me come in. Sorry, there is no E. That is A. That is A. Mu star A is less than or equal to mu of A. Correct? Okay. That's because you take, mu star A is defined as the infimum of a collection. And in that collection, this A, A union phi, the empty set is there. So because of that, by definition, mu star A is less than or equal to this. Now we want to prove that mu of A is greater than that. That's what we want to prove. Okay. So now to prove mu of A. And for that, we will always use the epsilon argument and other thing. So for that, what do we want to prove? So to prove this, enough to prove. So now, So what we want to prove, mu star A is greater than that. To prove that, we take any collection AN which covers A, okay, any collection AN in the algebra which covers this A. Then we take this sum. That sum, for any such sum, it is greater than mu of A. Suppose if you prove that, then if you take the infimum, that's also greater than that, right? Okay, the argument is clear. So suppose is in A, okay, that's right. Okay, A is A is contained in that. Okay, okay. Okay. Now, so how do we prove that? We want to prove that we want this. We want summation mu of an equal to 1 to infinity. This is greater than mu of a. That's what we want to prove. But then this is equal to so what? Yeah. So this is greater than. See, all this an contains a intersection an, of course. Okay. So because of that mu, so because of that mu of an, we have already proved this monotonicity is greater than or equal to mu of a intersection an. So this is greater than or equal to, though this implies this is greater than summation n equal to 1 to infinity mu of an intersection an intersection. Oh no, if I write something wrong, it's very difficult to change it. Yeah, an intersection a. Okay, because an contains this, mu of an is greater than that, so this summation is greater than that. So now that is greater than or equal to mu of a. Since, shall I rewrite it again? Maybe I will erase the whole thing and rewrite it again. What happened? We have an contains a intersection an. So mu of an contains this. So this implies summation mu of an n equal to 1 to infinity is greater than or equal to summation mu of a intersection an. Okay. But a, so then a is contained in union of a intersection an. I mean, it's equal to, sorry, it's equal to that. Okay. So because of that, mu of a, we have already the subadditivity. Mu of a is less than or equal to summation mu of a intersection a to infinity. So that's what we have there. So this implies summation n equal to 1 to infinity mu of, when did it change? We have proved this, okay? So because of that, this is true, okay? From this, we have proved this, and each I mean, this is less than or equal to this, so because of that, this is true. Okay. So this is true for all, since this is true for all collection, since this is true for all collection, for all AN contained in A, this mu star A is just the infimum of this. Mu star A is greater than or equal to mu of A. Okay. So the whole thing implies mu star A equal to mu of A for all A in the algebra A. Okay. I hope it's clear. If you want to go somewhere, I mean,
This is fine. This is fine.
this is fine. Okay. So that's what we have proved. Okay. So how much time I have? I have 10 minutes, 15 minutes nearly. Okay. So now we define some other collection of sets. We will prove that that's a sigma algebra, and we will prove that. So this is our aim. Next, our aim is this. Okay. Our aim, I have told our aim is to prove this. Okay. But we will prove something more, I said. We have already verified that this is equal to, I mean, we have already verified this. This is already verified. Oh, no. Yeah. Our aim is to prove 1 and 2. We have already verified 1. We want to prove 2. 2 is something to verify. Mu star restricted to sigma A. Sigma, the sigma algebra generated by is a measure. That's what we want to prove. But we will define a more general sigma algebra containing the sigma of A and prove that it's a measure on that sigma algebra. Okay. Okay. So for that, we define that sigma algebra. So we take the collection. So we define what is called a measurable collection. Okay. This is the definition. Okay. A subset A contained in X is mu star measurable. It's just a definition. Mu star definition measurable if so the subset is A if mu star E, I mean you take some other E equal to mu star of A intersection E plus mu star of A complement intersection E. You should remember that we are taking the complement with A. Okay, A satisfies that property. This is for all E. Okay. So all E. Okay. Okay. So you take you call a subset as measurable if it satisfies this additivity property. Of course, E is equal to, as I said, E equal to A intersection E union A complement intersection E as a disjoint union. Then it satisfies this additivity property. This A satisfies this additivity property for all E. Okay. This is what is called a measurable set. Then you want to take the collection. Okay. So let M of mu is the collection of all mu star measurable sets. Okay. Then we want to prove that this collection is a sigma algebra. That's what we want to prove. Okay. So to prove that, first we notice the following. We have proved that mu star is subadditive. Okay. Since mu star is subadditive, which we have already proved, that is mu star E. I mean, you know that the set E is equal to A intersection E union A complement intersection E. This is less than or equal to this mu star. So we have already proved this. So to prove this property, to prove A is measurable, I mean, I sometimes say just measurable when mu is there, okay? It's enough to prove mu star E. It's enough to prove this inequality, okay? Greater than.
Sir, where did we prove that this mu star is subadditive?
Just before, the earlier thing. The earlier lemma is that, no?
Like there, didn't we just prove that mu star A equals mu A for all A in script A?
What is the second assertion? 2. 2 is mu star is subadditive. Just go
I
behind.
don't think you have proved that second assertion.
Hmm?
You didn't
Oh, we
prove
didn't
the
prove that.
second one. I think.
We didn't prove that. Oh, forgot. Sorry. Oh, sorry. Yeah. So, do I have time to prove? Yeah, that is slightly involved. I'm sorry. You have to take epsilon. Oh, sorry. I just ran over. Okay, we will prove that first. Now, I'm sorry about it. I don't know. I just, yeah, we only proved that it is the first assertion we proved. We didn't prove the second statement. Okay. Yeah, we'll prove that. Okay. So if we prove that, okay, since mu star is subadditive, it's always enough to prove this. Okay. Mu star A complement intersection A. So it is enough to prove this. Okay. Now proof of subadditivity. Sorry. I'm very sorry about it. Proof of. I just said and I didn't prove it. Okay. Proof of subadditivity. Mu star. Okay, I may have to take a few. I mean, some time. Okay. So, what do we want to prove? So, suppose. So, suppose. I mean, it's true for union, but we take it like this. I mean, for a bigger set, it's. Now, this is what we want to prove. Suppose this is what is subadditivity. Did I say something else? Once again. Subadditivity. In my definition, I have said contained in that. Yeah, that's okay. What I have said is correct. Okay. Yeah, there's no problem in my definition. Suppose we call that as E here. That's all. Okay. N equal to 1 to infinity En. We call E to be this union of n equal to 1 to infinity. Then we want to prove. Okay. En. That's what we want to prove. Okay. So what do we have to prove? We want to prove that. So you know this epsilon trick. We will prove that this mu star summation mu star un plus epsilon is greater than this for all epsilon. Okay. Then you by for any arbitrary epsilon, then that will prove this inequality. Okay. So we have to use epsilon. So let epsilon greater than 0, something arbitrary. But we have n here, so we have to use epsilon by 2 power n, which will sum to epsilon. So choose a n k. Let epsilon greater than 0, then choose for n. Okay, you fix a n and n, of course. A and k, which is contained in k. Okay, such that en is contained in union of k equal to 1 to infinity a n k. N is fixed here, so the union is over k, and en is contained in this, and mu star en, which is the infimum. Okay, mu star en is the infimum. So mu star en plus I have to take epsilon, so epsilon by 2 power n. No, mu star en is what I want to approximate. Okay, so let me write it clearly. So what do we want to do? I want to, this mu star en, I want to say that this is the infimum of this, all this kind of union. So if I increase it by epsilon, there will exist something which will be less than that. Okay, that's what I have to do. So summation mu star a and k, okay, is less than or equal to k equal to 1 to infinity. Okay, is less than or equal to mu star En plus epsilon by 2 power n. This is okay. I'm saying that, no, this is, you forget about n. N is just to, for each En I am doing, I mean, so let me write it and we will erase it, okay? If you have any E, then this mu star E is just the infimum this mu star E is just the infimum of mu star of An, sorry, or mu of An, sorry. Here also it's mu. Okay. Mu of An with An, union of An. Union of An contains this E. This is the infimum. What is the definition of infimum? Infimum, you know the definition of infimum. It is just, I mean, infimum is not minimum. I hope, I mean, I'm sure all CMA students are used to that, but if others have a problem, I will go through this. I don't know how many of you are from other universities. If you have some problem, I have, see, infimum, what is the definition of infimum is this. If you take any epsilon, and if you, see, let's forget about this. Let us take any number. You take a collection, infimum of something, some numbers, you call some numbers, some x lambda, okay, some x lambda, lambda is in some set lambda equal to x. What does it mean? If for all epsilon greater than 0, okay, for all epsilon greater than 0, there exists a x lambda, okay, such that this x lambda is less than x plus epsilon. I'm using for positive, I mean real numbers, okay. That's what it means like that. If you increase the x by epsilon, okay, then there exists x lambda between this x and x plus lambda, okay, that is greater than x, and then it's like this. That is what it means by the infimum of x lambda is x. Correct? This is the definition of x lambda. Minimum is clear. You just look at the, if you have finitely many of them, then you can find the minimum, which is minimum is attained there. Infimum is not attained there. You have a collection x lambda, where lambda is indexed by this script, capital script lambda, capital lambda. Then this infimum is something which may not be contained in this x lambda. It may not be one of those x lambda. It is some other x. I mean, it may be attained. If it is a compact set or something, you know that it's attained. It may be attained. So that is this x, where this x is given by this unique property. That is, if you increase this x by epsilon, okay, then between x and x plus epsilon, there will be exist some x lambda. That is the definition of infimum. Okay, so I am just using this definition. Okay, this is the definition of infimum, and using this definition, this mu star En is just the infimum of all this collection. So if I increase this mu star En by epsilon by 2 power n, epsilon can be anything, epsilon by 2 power n, then I will get a collection of this A and K such that it satisfies this property. Okay, so I have written it correctly. There is no problem. This is the definition. Okay.
So here you are assuming that mu star n is finite, right?
Mu star En is, if it is, yeah. If it is infinity, then everything will become infinity, so it will be satisfied. So, right?
Okay, yes.
So that is not a problem. You first consider that case and forget it. Let's not write each and everything, so it will be very long. So the infinite case is okay. So that is not a problem. So if it is not infinity, you assume that it's finite, then that is satisfied this. Okay, this infimum is attained like this. So now you sum over k also. So what is that you want to prove? You want to prove that now this E is contained in union of k equal to 1 to, sorry, yeah, k, it's okay. Maybe I will change it. Which way? N equal to 1 to infinity, k equal to infinity. I have written A, no? So, yeah, A and k. Okay. Now mu star E, this implies is, I mean, all this A and k are in the algebra A. By definition, this is less than or equal to summation n equal to 1 to infinity, summation k equal to 1 to infinity, mu of A and k. Okay. That's right. So, but then we know that all this mu of A and K, so that's right. All this mu of A and K is less than or equal to summation n equal to 1 to infinity, which is which is less than or equal to, further less than or equal to mu star En plus epsilon by 2 power n. But epsilon by 2 power n will sum to epsilon. So this is less than or equal to summation n equal to 1 to infinity mu star En plus epsilon. Okay. This is true for all epsilon greater than 0. So this implies my time is over. So this implies mu star E is less than or equal to summation n equal to 1 to infinity mu star E. So we approve. Okay. So any problem? So my battery is going in my laptop. I have to connect it. The plug point is not here. It's somewhere else. So it may go off in one minute or something, 5 minutes or something. So if it goes off, then the class is over. Anyway, the time is up. If you want to ask something, you can ask now. Okay. So we approved subadditivity. Everything is clearly
Sir,
written.
instead of posting the notes in the mailing list, can you post them in some separate site or something?
Which one? The notes?
Yeah, all the notes. So it's easy to access. Otherwise, I did
Okay, I can send it. I have to find it out how to send it. See, there is some problem. I have to buy a cable to connect my iPad to my laptop. I'm not able to send file. I have to sort it out. I just bought it. So
maybe you can create a module on Moodle and then upload the notes on Moodle.
Yeah, that I have to again. I haven't still tried it. Okay, I will send it by email once I get it in my laptop. Okay. Yeah, I think I can send this file also. That's not a problem. Okay.
Yeah, thanks.
Okay. So, but it's always better you take the notes. Okay. Yeah.
Excuse me. Are you going to have some LaTeX? Formally written notes
No,
like?
no, certainly not. No. These things are available in the book everywhere. So I'm not going to write it. Yeah, I'm not going to do that. Okay. So if everything is clear, let us end the class. Okay. Goodbye.
Sir, what about the presentations?
Yeah, I will tell in the next class. Okay. There is maybe one of you, I will write it. I will write it or send the notes. So everybody got the book by Sundar Shivatraya. You can look at that, or you can look any other book. I will send the notes. So next week, we will start from next week. Okay. Okay.
So what is the mechanism going to be? So you will give each one of us a topic and
something, and you will choose. Whoever opts for it first, they will present it, or you can discuss among yourself and change topic if you want. Then you can present. This is just to make sure you understand the theory also, because in the exam I will be asking only questions, and I don't know. So today participants are 18. So I don't know how many people are going to register. So it's good to have good attendance, because if attendance getting low, then I may give marks for attendance. Okay, so it will not be too much, but there will be some marks. So it's better to attend. Yeah, I will tell you next week what to present. Okay. Okay.
Okay, sir.
Okay. Bye. Goodbye. I'll end the meeting.
Thank you, sir.
Okay. Bye. Thank you.
Can I leave now?
Yeah.
Can I leave now?
Yeah. Sure. I'll just.
Sir, and another thing. Today I had sent you my assignment via another email. So
I will take care of it. Yeah. Next time when you send it as a reply to the earlier mail. Only, the reply only to me. Yeah. Okay.
Okay. So this one I don't need to resend, right?
No, you don't need to. Okay.
Okay, sir.
Okay. Bye.